Imagine you're sitting in a garden on a warm afternoon in 1666. The Black Plague is ravaging London, universities are closed, and a 23-year-old Isaac Newton has returned to his mother's house in the countryside. He's contemplating the mysteries of motion when... Now, contrary to popular belief, that apple didn't bonk Newton on the head. But what it did do was spark one of the most revolutionary insights in the history of science. Newton began wondering, what if the force pulling that apple down is the same force keeping the moon in orbit around Earth? This single moment of curiosity led to 3 fundamental laws that govern everything in motion around us, from the coffee cup on your desk to rockets launching into space. Let's dive into Newton's 3 laws of motion. Newton's first law. Let's start with Newton's first law, also known as the law of inertia. And here's where things get interesting. This law has been mistranslated for over 300 years. The traditional translation says, a body at rest stays at rest, and a body in motion stays in motion, unless acted upon by an external force. But the correct translation is, a body at rest stays at rest, and a body in motion stays in motion, except insofar as it is acted upon by external forces. That tiny word change, from unless to except insofar as, completely changes the meaning. The traditional version suggests objects only move when no forces act on them. But think about it. When is anything completely free of forces? Your phone right now has gravity pulling it down, the table pushing up, air molecules bumping into it. According to the traditional translation, it should be impossible for your phone to stay still. The real first law says objects continue their motion, whether at rest or moving, except insofar as forces make them deviate from that motion. Take a spinning top. Newton himself used this example. The top keeps spinning and spinning, except insofar as friction and air resistance slow it down. Remove those forces, like in space, and it spins forever. This is inertia, the tendency of objects to resist changes in their motion. More massive objects have more inertia. That's why it's harder to push a car than a shopping cart. Newton's second law. Now we get to the mathematical heart of motion, Newton's second law. This is where Newton got genius-level specific about how forces change motion. Force equals mass times acceleration. Simple equation, profound implications. But let's build this from scratch to really understand what Newton was thinking. Newton actually started with momentum, mass times velocity. He realized that force causes the rate of change of momentum. For objects with constant mass, this simplifies to our familiar force equals mass times acceleration. But what does this really mean? Let's break it down with some mind-bending demonstrations. Picture 2 boxes. One weighs 1 kilogram and another weighs 10 kilograms. Apply the same 50 Newton force to both. The 1 kilogram box accelerates at 50 meters per second squared, while the 10 kilogram box accelerates at only 5 meters per second squared. Now take the same 5 kilogram box and apply different forces. 10 newtons, 20 newtons, 50 newtons. You get accelerations of 2, 4, and 10 meters per second squared, respectively. Notice the beautiful relationships. Double the force, double the acceleration. Double the mass, half the acceleration for the same force. This isn't just math, this is the universe's operating system. Here's a crucial misconception to avoid. Force determines acceleration, not velocity. Watch a car turning a corner at constant speed. The car's speed is constant, but its velocity is constantly changing direction. The centripetal force points inward, causing inward acceleration, even though the car moves tangentially. Force equals mass times acceleration, and acceleration includes changes in direction. Hey, if you're enjoying this deep dive into Newton's laws, hit that subscribe button and give this video a thumbs up. It really helps us create more physics content like this. And don't forget to share this with anyone who's curious about how the universe works. Now, let's tackle the third law. Newton's third law. Newton's third law might seem simple at first. For every action, there is an equal and opposite reaction. But this law reveals something profound about how forces actually work in our universe. When you walk, you're not just moving forward, you're pushing the Earth backward. Of course, Earth is so massive that its acceleration is negligible, but the force is there. And here's something cool about rockets. They don't push against air, they push against their own exhaust gases. That's why rockets work perfectly in the vacuum of space. Now here's where nearly 100% of students get confused. They think, If action-reaction forces are always equal, how does anything ever move? The forces are always equal. The secret is that action-reaction forces act on different objects. When you push on a wall, you and the wall experience equal forces, but the wall is connected to the earth, giving it enormous inertia. The net force on you might be unbalanced, causing you to accelerate backward. But the action-reaction pair itself? Always equal, always opposite. The Earth pulls on the Moon with exactly the same force that the Moon pulls on Earth. The difference? Earth has 81 times more mass, so it accelerates 81 times less. But the gravitational forces? Perfectly equal. Let's see all three laws working together in a rocket launch, one of humanity's greatest applications of Newtonian physics. First law in action. The rocket stays on the launch pad at rest until the enormous thrust force overcomes gravity and air resistance. Second law in action. The net upward force creates upward acceleration. As fuel burns and mass decreases, the same thrust creates greater acceleration. Force equals mass times acceleration in real time. Third law in action. Hot gases shoot downward, pushing the rocket upward. Equal and opposite forces, but acting on different objects. These three laws, conceived by a 23-year-old during a plague lockdown, became the foundation for our modern technological world. Without understanding Newton's laws, we couldn't have GPS, space travel, or even properly designed car safety systems. So the next time you see something in motion, or staying perfectly still, remember Newton's insights. That simple apple fall revealed the universal principles governing everything from subatomic particles to galaxies. But here's the beautiful irony. Newton's laws aren't the end of the story. They work perfectly for everyday speeds and sizes, but at the speed of light or quantum scales, we need Einstein's relativity and quantum mechanics. Newton gave us the keys to the classical universe. What other mysteries are waiting for the next curious mind asking the right question? If this journey through Newton's laws sparked your curiosity, please hit subscribe for more physics deep dives. Like this video if it helped you understand these fundamental laws, and share it with fellow science enthusiasts. We've got quantum mechanics, relativity, and so much more coming your way. Until next time, keep questioning, keep experimenting, and remember, every force has its equal and opposite reaction, including the force of curiosity that drives us to understand our amazing universe.